I am Riya Muskan, roll number 16.
Everyone, myself Varun Patel. My roll number is 18.
My name is Mukul Rajput and my roll number is 17. Our project name is Real Time Multi-Threaded Application Simulator. So the problem statement is operating systems run multiple tasks at the same time using threads, but it is hard to understand how threads are managed, scheduled, and synchronized just by reading a theory. This project builds an interactive multi-threading simulator in C using GTK-3 that shows in real time how threads move through different states and how synchronization tools like semaphores and monitors works.
I will be presenting the core functionality of our real-time multi-threaded application simulator focusing on multi-threading models, scheduling, and synchronization. The simulator supports three multi-threading models which can be selected from this drop-down menu: many-to-one, one-to-one, and many-to-many. Each model defines how user-level threads are mapped to kernel threads directly impact system performance and concurrency. Through this interface, we can observe how different models behave under execution and how efficiently threads are managed. I will be selecting many-to-one for this demo run. And now I'll demonstrate how the simulator works. I'll start by creating multiple threads. Each thread represents an independent execution unit. Now I'll press the start button to see the simulation in real time. Now you can see that threads move between different states such as ready, running, and waiting. These transitions are updated dynamically, allowing us to visualize how the CPU handles multiple threads simultaneously. The simulator uses round-robin scheduling where each thread is assigned a fixed time quantum. As execution progresses, the CPU switches between threads after each time slice, which ensures fair allocation of CPU time. If we adjust the time quantum, we can observe how the frequency of context switching changes. As you can see, all the four threads have terminated after completing their processing. Now, when multiple threads try to access the shared resources, synchronization becomes essential. We can implement the same using this drop-down menu using two options: semaphore or monitor. I will be using semaphore for this particular demo run. I will be creating threads to see the execution and clicking on the start button. Here we implement semaphores which control access by limiting how many threads can enter a critical section at a time. We can also use monitors as mentioned earlier, which ensure mutual exclusion and safe communication between the threads. Both of these prevents issues like race conditions and ensures correct execution of the code. It can be seen from the event log that the semaphores have been acquired and released by the threads when leaving or entering the critical section. From a technical perspective, the project is implemented in C language using the POSIX threads for multi-threading, GTK-3 for the graphical interface, and Cairo for real-time visualization. With this, I will be concluding the demonstration of the system's core functionality.
We also used round-robin scheduling where each thread gets equal CPU time, making simulation fair and realistic. One of the key parts of our project is synchronization. Using semaphores, we ensure that only one thread can enter the critical section at a time. With monitors, we demonstrated how threads wait and signal each other using condition labeling. These concepts are usually difficult to understand, but our visual interface makes them very clear. The simulator also includes features like Gantt charts, ready and waiting queues, CPU utilization, and step-by-step execution, which helps user observe everything in real time. Overall, this project helps us gain a strong practical understanding of operating system concepts, especially multi-threading, scheduling, and synchronization. It can also be used as a learning tool for students to better understand these topics.